of the interesting features about studying the impedance matrix or the admittance matrix was that we could look at the matrix and discern certain physical attributes about the network without knowing anything other than the impedance or admittance matrix itself. For example, if we looked at the impedance matrix and found that every single element was purely imaginary, the real part of every transimpedance parameter were equal to 0, then we conclude that that device must be a lossless device. It has no way to absorb energy. Conversely, if the device is lossless, has no resistor, no way to absorb energy, each element of the impedance matrix itself must be purely imaginary, have a real component which is equal to 0. So it's if and only if that those two things are related. Also, we talked about reciprocity, and reciprocity is a general property for the relatively simple devices and materials that we use in microwave engineering. It's hard to mess up reciprocity. And reciprocity will exhibit itself in terms of the impedance matrix, in terms of being symmetric. If Z12 is equal to Z21, for example, then, and that's true for every off-diagonal element, the corresponding on the other side is the same, the matrix is symmetric, then we know we have a reciprocal device, and if the device is reciprocal, it must result in a symmetric matrix. So the question is, how do those physical attributes manifest themselves with respect to the scattering matrix? And in one case, the result is precisely the same as with the impedance or admittance matrix. In the other case, it's a very different kind of result that we shall see. Moreover, there's another characteristic that we care about with respect to microwave components that we didn't discuss because we didn't care about with respect to the impedance matrix or the admittance matrix, and that is the idea of a matched device. We can determine whether a microwave device is matched by the elements of the scattering matrix. Moreover, we know a matched device must have a certain characteristic with respect to the elements of the scattering matrix. So the idea of a matched device can likewise be discerned by looking at the scattering matrix of that device. So let's go back and recall what is a matched device. What do we mean when we say quote-unquote matched device? And again, this causes confusion with students, this idea of match, and what does it mean with respect to conjugate match, and are they the same thing? And of course, they are not the same thing. We need to understand what a matched device is. We've talked about a matched load, we've talked about a matched source, but we can also talk about multi-port devices being a matched device. And we really need to make sure we understand what that means. We had a section on matched device. Go back and review that if you need to. But basically, if we have a multi-port device, in this case a 4-port device, and we immerse this 4-port device in a matched system, in other words, we connect it to other devices that are also matched, and we connect them with transmission lines that are numerically have a characteristic impedance that are numerically equal to the value to which the device is matched, then we find at every port impedance, be it the input impedance or the output impedance, if it is supplying energy, if energy is coming out from the device, that port impedance will likewise be numerically equal to Z0. Now, the easiest way to test this would be, let's say, take a 4-port device and put a matched load on each of the 3 ports. Now, this, yes, could be simply a resistor numerically equal to Z0, but in a more realistic scenario, what these would represent would be the input impedance of other matched devices. And if they are other matched devices and connected to in a completely matched system, then those input impedances will likewise be equal to Z0. So we can think of this as immersing this 4-port device in a matched system. Matched devices connected with transmission lines of characteristic impedance Z0, the value to which they are, quote, matched. So in this case, again, we'll just put resistors numerically equal to Z0 here, and so gamma L is equal to 0. If we have a matched 4-port device, then the input impedance we'll see here will be equal to Z0. It will be numerically equal to the characteristic impedance of the transmission line. The input reflection coefficient with respect to Z0 there is going to be equal to 0. Now, this is true only if we connect it to a matched system, if we immerse it into a matched system. If, for example, we connect matched loads here. If we took these matched loads off, if we made gamma L something other than 0 here, what we'd find in that case is Zn is not equal to Z0. Now, that doesn't mean that this device is not a, quote, matched device. A matched device doesn't say that the input impedance is Z0 regardless of what's connected to the other ports. That's impossible to have a situation where when possible. It's not possible for a useful device for that to occur. So if we don't take a matched device and immerse it in a matched system, we're not going to have an input impedance numerically equal to 0. But if we do, we will have one equal to 0, 0. If that's true, then we have a matched device. This is true for port 1, but it must also be true for port 2 and port 3 and port 4. Moreover, if we went through and we took off a matched load here and we put a matched source here, again, which would be the equivalent circuit for some system that likewise would be immersed in a matched system there. If we have a matched source, a source impedance of Z0, what we'd find is that we did equivalent to Thevenin's equivalent of the entire thing, the output impedance would be equal to Z0. The equivalent source, if there was a matched source here, a matched load here, and a matched load here, this equivalent source would likewise be a matched source. Its output impedance would be equal to 0 if this is a matched device. And that's the key thing about a matched device. You immerse it into a matched system, a system connected with transmission lines of characteristic impedance Z0, and all of the other devices are designed such that they will exhibit output and input impedances numerically equal to Z0 if immersed also in a matched system. Then we have what's called a matched device. Again, it can't force the input or output impedance to be Z0 if you connect the wrong things to it. But if you connect matched devices to other matched devices, then all the impedances will be numerically equal to Z0. What that means is then we can connect matched devices to other matched devices with transmission lines equal to, with a characteristic impedance of Z0, and preserve a conjugate match. All the available power of every matched source will be delivered then to every matched load when we connect matched devices to each other. It only takes one non-matched device, some weird device here where gamma L is equal to 0.6 or something like that, to mess up the whole thing, where now all of a sudden the impedances are no longer equal to Z0, input or output impedance, and the power transfer we get from one port to the other is not going to be equal to the available power, and it will depend on the length of the transmission line. So again, a matched device can't fix a mismatched system. It preserves the matchedness if we connect other matched devices to it. So this is a key parameter we want in our microwave devices. We want our device to have be a matched device, one that we can connect to other matched devices with the characteristic impedance transmission line Z0. And so we seek out devices like this if we're going to attach them together. And we're trying to design devices that are, quote, matched devices, so we can do this, connect them together, and get a preserved conjugate match regardless of the length of the transmission line. What scattering matrix are we interested in that will preserve this characteristic of a matched device? What should the parameters be? Can we recognize it if we see it? It turns out we can. So think about what we did in this the last slide there. We took a 4-port device and we terminated 3 of the ports in matched loads. And then it left us with the port at the port 1, and we said that the input impedance must be equal to Z0 if it is a matched device. Well, this is very similar to the experiment that we used to determine our values of scattering parameters. If we wanted to go through and find S11 and S21 and S31 and S41, what we do is put matched loads at the other 3 ports and put one incident wave at port 1. So that's, again, a similar thing that we do for the scattering parameter. Now, what would the scattering parameters be if we had a matched device? More specifically, what would the scattering parameter S11 be if we had a matched device? So we go through and we put matched devices, matched loads at all the other ports, and we say that the input impedance at port 1 must be equal to Z0. In other words, its input reflection coefficient is equal to 0. Well, what does that mean with respect to the scattering parameter S11? S11 is the ratio then of the scattered wave at port 1 to the incident wave at port 1 when all the other ports are terminated in matched load. If the device, the 4-port device, is a, quote, matched device, then the input impedance will be Z0, the reflection coefficient will be 0, and therefore there will be no scattered wave from port 1. Nothing will be reflected. There will be an incident wave at port 1, but because the input impedance is Z0, the input reflection coefficient is equal to 0, nothing will be reflected. A matched device will have a scattering parameter of S11 is equal to 0. That's true for the port 1, and also if we repeat the experiment for port 2. We put matched loads on all the ports except for port 2. We put an incident wave onto port 2. What will be the reflected wave? If it's a matched device, the input impedance is Z0. The reflection coefficient there is equal to 0. None of the incident wave is reflected because, again, the input impedance is Z0. And so S22 would be equal to 0 for that case. Likewise for port 3 and port 4. Generally speaking, then, for any number of a port device, a device is considered to be a matched device, one whose input impedance or output impedance will exhibit a value of Z0 if immersed in a matched system. That will exhibit itself with respect to the diagonal elements of the scattering matrix. S11, S22, S33, S44, all of them, every one of them must be equal to 0. Not just some of them, all of them. If every element of that diagonal elements of the scattering matrix are equal to 0, then and only then can we say we have a matched device. Moreover, if we have a matched device, then every one of those diagonal elements will be equal to 0 itself. So here's an example of a scattering matrix now, which is the scattering matrix of a 3-port device, which is a matched device. And again, this we can tell this because the diagonal elements are all equal to 0. S11, S22, S33, every one of them, all of them, are equal to 0. And again, this means that if we attach this 3-port device to other matched devices, other devices whose diagonal elements of the scattering matrix are equal to 0, then we will preserve then a conjugate match, a maximum power, all the available power of the matched sources, equivalent match sources will be delivered to the devices regardless of the length of the transmission line connecting them, as long as the transmission line is likewise equal to Z0. So that's what we're looking for, is devices that will play well together, that we can connect them with characteristic impedance transmission lines of Z0, and that will preserve maximum power transfer. In other words, all the available power of any device will be delivered to the load, the equivalent input impedance of every other device. So the first of all result is if we have a matched device that exhibits itself as a scattering matrix whose diagonal elements are equal to 0. Let's move on and ask ourselves, what would a scattering matrix look like for a device that was lossless? Completely lossless. And we know what that means. Remember, we talked about this for impedance matrix, admittance matrix. It is a device that is made up completely of reactive elements, elements that cannot absorb energy. So there are no resistors that would be inside a lossless device. We might have inductors or capacitors. More specifically for microwave engineering, almost certainly we'd have links of lossless transmission lines. And if we have links of lossless transmission lines in our circuit, exclusively in our circuit without resistors, we have a lossless device. So what would a scattering matrix look like for a lossless device? Remember, for impedance admittance, it was pretty simple. If every element is purely imaginary, therefore it's lossless. With respect to scattering matrix, there's no such equivalent or simple statement. There is a way that we can determine whether a device is lossless or not by looking at the scattering matrix, but it's a little bit more complicated and involved than simply determining whether the elements are real and if the elements are purely imaginary. To understand this result that we're going to find with respect to a scattering matrix of a lossless device, we need to go through and talk about power with respect to our scattering parameters. Now, I probably should have put this section in its own section so you can see the relationships here. This section by itself is very important, even if we weren't trying to determine the form of a scattering matrix of a lossless device. So pay attention to this section here, because we're going to talk about conservation of energy and energy flow, the rate of energy flow in and out of a device by using the scattering parameters of that device. So the first thing we start with is we want to know at what rate is energy being carried into the port, incident on a given port. So we have a port 1, or port M, I should say, and we want to know what is the power associated with the incident wave, with the plus wave in this case, since we've defined Z is increasing toward the port. And we found earlier that we could take the magnitude squared of our A normalized wave amplitude, take the magnitude squared of this complex value A, evaluate at the port plane, the magnitude squared divided by 2, and that is the power associated with that incident wave. Likewise, for the exiting wave or the scattered wave from some port, we take the normalized scattered wave amplitude B, complex number, until we take the magnitude squared divided by 2, and that is the rate of energy flow associated with that minus wave, the wave exiting the port, the wave scattering away. So we have energy flow toward a port, and we have energy flow away from the port. And of course, the key thing here is the net energy flow from a port. And this is just like we did on a transmission line. We had the plus wave energy and the minus wave energy. The difference between the two, of course, was the net energy flow along that transmission line. Energy going one way, energy going the other. The difference is the net energy flow, the rate of energy flow. And so we're going to define the same thing here, a delta P for each of the ports, and really each of the transmission lines that are flowing toward the ports. The difference between the plus wave, we'll define it in this way, the plus wave power minus the minus wave power is what we're going to call a delta. And so in this case, if our delta is positive, it means that the plus wave power is larger than the minus wave power. It can be negative if in fact the minus wave or scattered wave power is greater than the incident. And that can happen. We can have a lot more power coming out of a port than is going into it. The real physical power, though, the rate of energy flow into a port, is the difference between the two. We have incident, we've reflected. The difference is really the physical rate at which energy is entering a port or exiting a port, not associated with the incident wave or reflected wave, but in fact the difference of those two values, which are provided here. Okay, so we've defined the incident power, the plus wave power for each port, and the minus wave, the scattered power for each port, and likewise a net power for each port, the difference between incident and scattered, or incident and reflected there. And now let's put these pieces together to do an analysis that's ultimately going to be dependent on conservation of energy. The thing about a lossless device is it can't absorb any energy, so the rate at which energy goes in must be equal to the rate at which energy goes out. And that's the key for us to determine what the scattering matrix of a lossless device should look like. All right, so we're going to start here with a total incident power. We're going to sum the power associated with each of the incident waves on each of the ports. So this is the power associated with the normalized wave function A, wave propagating toward the ports. And so we're going to add them all together, and we're going to say this is the rate at which energy is being carried toward the device, carried by the incident waves propagating toward the device. Now, we can take this term here, notice the sum of the magnitude squared of each element A sub m, and because we defined a data vector, which is the value of each complex value A for each of the ports, A1, A2, A3, we can see that the sum of the magnitude squared of each of these can be written in linear algebra in this form. And this is, H is what we call a Hermitian transpose operation. So this is a vector A, and we go through and we take the transpose and think of it as taking a column vector and making it into a row vector. And then we go through and we take the complex conjugate of each of those elements. And then we multiply that times the column vector A. And so we get a take A and take the Hermitian transpose and make it into a row vector with the complex conjugate, and then we multiply it by the other vector A there. And really this is a dot product. If you're familiar with dot products of going through and multiplying each element together with itself and then adding them all up, in this case we take the complex transpose, the complex conjugate rather, of each of the elements, of one of the elements rather, before we multiply it by the other. So this is an inner product, a dot product, a scalar product operator that hopefully you've seen things like that before. So this is the notation we have, a conjugate transpose or Hermitian transpose operation. We've just used our linear algebraic form to write all of this in this shorthand. So we take the inner product of vector A with itself, the Hermitian transpose of A with vector A, and divide by 2. And we know that's equal to this, which is then the total incident power. We've summed up the power associated with each of the incident waves that are propagating toward the device. We can do the same thing with respect to the scattered waves. There are scattered waves from each port, exiting waves from each port, and we can determine the power associated with each of these exiting waves from the normalized wave function B. And take the magnitude squared of them and divide by 2. We add them all up, and just as we did for the previous case with the incident waves, we can show that we can write that in a linear algebraic form regarding the B vector, the data vector of all of the normalized scattered wave amplitudes, B1, B2, B3. And so we get the same result as we might expect. We look at these two equations and we see that they're the same thing with except for A then gets mapped onto B, and so we would get the same result in this bottom case. Of course, we know that our B vector and our A vector are related by the scattering matrix. And so this is, again, the linear algebraic shorthand that relates all of the normalized incident wave amplitudes to the normalized scattering wave amplitudes based on the scattering matrix. Now, we know that from that we can see that the Hermitian transpose of B is going to be the Hermitian transpose of S times A, and if you're familiar with linear algebra, we can go through and show that that is equal to the Hermitian transpose of A times the Hermitian transpose of H. Why do we care? Well, let's go back to our power associated with the scattered waves. This is a sum of the power associated with each of the waves scattered from the ports. And we found that it was equal to this. It'd be written in terms of the B vector in this form. But now we've written this B vector in terms of the A vector in the scattering matrix. Likewise, Hermitian transpose in terms of the A vector in the scattering matrix. We put both of those pieces in here and we have this result. The power associated with the exiting waves, the total power associated with all the exiting waves, written not in terms of the normalized scattered wave amplitudes, but written in terms of the normal incident wave amplitudes A, along, of course, with the scattering matrix. So now let's go and determine the total net power. Now, there's two ways of doing that. We can go through and sum up all of the power associated with the incident waves and then subtract it from the summation of all the power associated with the exiting or scattered waves. And so we take P plus minus P, and again, this is the total summed over all the ports, and that would be then the total net power flow into the device. The alternative way of doing that is taking the net power flow associated with each port. What is the difference between incident and scattered? That is the net power flow into, if positive, and out of, if negative, each of the port. And we can add those all together. Again, some of these values could be or will be positive if the net power flow is into the port. Some will be negative if the net power flow is out of the port. But we add them all together, and that is the net power flow into our device that we have. Again, we can calculate either way. And the result, though, when we take our previous results for the incident power, total incident power, the total reflected power, put them together, and we can write it in this form. And this I here is the identity matrix. If we take A and multiply by the identity matrix, we still have vector A. That's the nature of the identity matrix. And so the net power flow into our device is equal to this. Now, the important thing here is to understand what is this net power flow. If this net power flow turns out to be positive, that means that energy, the net power, is going into that device. what happens to it? Well, if the net power flow is positive, that means that device has to be absorbing that net power flow. Every second we have 23 millijoules of energy that flow into this device, the net. Yes, we have things that are flowing out and scattered and things that are coming in terms of incident. But if we take the difference between the two and that result is a net positive, that means stuff is going in. The net power is going in. It has to be absorbed in that case. If we go through and find that the net power flow is negative, then that means that we have a situation where the device is absorbing negative power. What does that mean? Well, it means it's actually producing energy. It must be an active device. And so it's important that you really understand what this delta P is telling us. Whether it's positive, it's absorbing energy. If it's negative, it is producing energy. And of course, the question is, what if it's zero? It's neither absorbing energy nor is it producing energy. And of course, if our device is not absorbing energy, it's not dissipating energy, and it's not creating energy, then it is by definition a lossless device. If a device is lossy, it can have a net power flow which is positive. The power flows in at a certain rate and it gets converted into heat. The electromagnetic energy, again, turns into heat. If it's a negative net power flow, then it must be an active device. Energy is flowing out of it. There must be something, ultimately a DC source of energy that's being converted into a microwave source of energy. But for a lossless device, it's a passive device, can't create energy, can't destroy energy. And therefore, conservation of energy must be preserved. The rate at which the incident waves are carrying energy toward the device must be precisely equal to the rate at which the scattered waves are carrying energy away from the device. In other words, the net power flow into the device is zero. It's neither absorbing energy or creating energy. It is in an energy balance. Again, this doesn't mean that there's no power, no energy flowing into port 1 or port 2 or port 3. We may have lots of energy pouring into port 1. It just means that we have to have an equal but opposite amount of energy pouring out of some other port or set of ports so that the net power flow is in balance. The net power flow is equal to zero. That's the definition of a lossless device. What does this statement mean to us mathematically? Well, we can take all of our mathematical results now, and we see that the net power flow for a lossless device must be equal to zero. Yet this is the net power flow for any device. And so we say for a lossless device, this equation must be equal to zero. Now, if we look at this, the A are the incident waves. They're not going to be zero. There's no reason for them to be zero. In fact, it would be a very uninteresting problem if there was no power flow incident on our lossless device. So in other words, for this equation to be equal to zero, the only way that can occur in any useful sense is if this term here is equal to zero. If the identity matrix minus the scattering matrix Hermitian times itself is equal to zero, then we have a lossless device. A lossless device must have a scattering matrix which satisfies this equation. We can go through and rewrite this in this form, which would be probably an easier way of stating it, that when we take the Hermitian transpose of the scattering matrix and multiply it by itself, the result must be the identity matrix. Identity matrix whose size, of course, then is going to be the same size as the scattering matrix, and n by n, where n is the number of ports of that device. So fortunately, a square matrix that has this property where we can take its Hermitian transpose and then multiply that by the matrix itself, and the result is an identity matrix. That seems sort of esoteric and convoluted and not very useful, but this actually is a kind of matrix that shows up quite a bit mathematically. A matrix, a square matrix that satisfies this equation, is known as a unitary matrix. And so we can make a statement that if a network is lossless, if a multi-port device is lossless, then its scattering matrix will be unitary. Moreover, if a scattering matrix of a device is unitary, then we can state without any other knowledge of that device that it must be lossless. That inside, we don't know what the circuit is in there, but it doesn't include anything that can absorb energy or create energy. So, how do we recognize a unitary matrix when we see one? The key thing in a unitary matrix are the columns. We talked about this before. The columns of a scattering matrix are very important. This is the result of our first experiment. We put one incident wave and only one incident wave on port 1. All the other incident waves on the device are equal to 0, and we see what scatters out of each port, and from that we can determine the first column of our scattering matrix. Then we put an incident wave on port 2 and make sure there's a matched device or matched load on all the other ports, so there's no other incident wave other than that in port 2. And we can see what scatters out of each port then, and that can determine the second column. And then likewise with an incident wave on port 3 and port 3 only, and port 4 and port 4 only. Each of these 4 columns in the scattering matrix represent the 4 experiments, the 4 evaluations that we do for the case where there's an incident wave and only one incident wave corresponding to each of the individual ports of that matrix. And these columns then are the key to understanding what is a unitary matrix. Because it turns out a unitary matrix is a square matrix whose columns form an orthonormal set. All right, so we say a lossless device has a scattering matrix that's unitary. Mathematically, that's correct, but what does that mean exactly? Well, we say a unitary matrix is one whose columns form an orthonormal set. Well, what does that mean exactly? Hopefully you've seen the idea of orthogonal vectors and normal vectors before, and if we have a set of vectors that are all normal and are mutually orthogonal, then we have an orthonormal set. First of all, what do we mean by a vector that is normal? A vector that is normal is one where if we go through and add up the magnitude squared of each element in that vector, the answer is 1. And in this case, what we're doing, the vector that we're adding up the elements are the, let's say, the first column vector of the scattering matrix. We would go through and take the magnitude squared of S11 plus the magnitude squared of S21 plus the magnitude squared of S31 plus the magnitude squared of S41 and so forth until we ran out of ports. We had the right number of ports. And if we add them all together, then the value is equal to 1. And that's true for every column vector in our scattering matrix, whether it's the first column vector, the second column vector, the third column vector. If we go through and we take the magnitude squared of each element in that column vector and add them up, we get a value of 1. Now this is the same thing, of course, as taking then the dot product or inner product of each column vector with itself. Hermitian transposed when we do that dot product. And so we say that vector has a magnitude equal to 1. Normal means it's normalized or has a value equal to 1. Orthogonal means, two vectors that are orthogonal means that if we go through and we take the first element of one times the first element of another, take the complex conjugate of 1 before we do that and multiply them together, and then take the second element complex conjugate times the second element of the other vector and multiply them together, and the third complex conjugate and the third multiply them together and then add them all up, the result is 0. Again, what we're really doing is taking a dot product, inner product between two vectors. And when we take the inner product, the dot product, in this case with the complex conjugate on 1, the Hermitian dot product, we take the dot product of the two vectors and we get 0. What do we say about those two vectors? We say those two vectors are orthogonal to each other. And so this is an abstraction that we have. We understood it when we were talking about unit vectors, perhaps in three-dimensional space, the idea of orthogonality, but we can extend this to more abstract mathematics as we've done here. If any two vectors that we grab are orthogonal, every two vectors that we grab, and these are column vectors in the scattering matrix, are orthogonal to each other, then we say they are mutually orthogonal. Every vector is mutually orthogonal to every other vector. In addition, if each of those vectors, those column vectors that we have, again, of the scattering matrix, if those are normalized, they have a magnitude of 1, then we say the set of vectors, and again, these are the column vectors in our scattering matrix, that set is orthonormal. Normal meaning the magnitude of each is 1, orthogonal means that the inner product of each is going to be 0, orthogonal to each other. And that's how we determine whether a matrix is unitary. We look at each column and see if the magnitudes are all equal to 1. If that's the case, then we start looking at the pairs of vectors, column 1 and column 3, and column 2 and column 4, and column 4 and column 1, and see if they're orthogonal. If every one of those possible pairs is 0, and every one has to be 0, if that's true, then our scattering matrix is unitary, and therefore that scattering matrix represents a lossless device. Moreover, if we have a lossless device, it must have a scattering matrix that's unitary. The columns of that scattering matrix must be orthonormal. So the question is, why must this be true? Why must a lossless multiport network exhibit a scattering matrix which is unitary? Why must it have columns which are orthonormal? Now, this is, we prove that this must be the case, but what's the physical rationale for that result? We can go through and look at least the normal part of it and see why the vectors must be normal. Their magnitude must have a value of 1, and we can do that by using conservation of energy arguments. And so let's say we have power incident on one port, and all the other ports are terminated, I should say terminated in matched loads, and so there's no other incident wave on our ports other than the one at port 1. So in that case, we can determine then the power of the scattered wave or the exiting waves at each of our ports. We can do that because we know the scattering matrix. We know that the wave exiting port M, for example, is the magnitude squared of the normalized wave amplitude B, subscript M, all right, the normalized wave amplitude on port M there. But we know because, and only because, we have one incident wave and one incident wave only, we can directly determine this value of B in terms of our lone incident wave A1. And we do that by multiplying by the scattering parameter SM1. So in this case, this is an element of our first column. The experiment we're doing is we're putting an incident wave on port 1 or toward port 1, and so the elements of that first column are going to be in play here. And so this could be the, let's say, the power associated with the scattered wave at port 3. M is equal to 3, so this would be S31, for example. Multiply that by A1, that gives us B3, the normalized wave amplitude coming out of port 3. Again, this is because we only have one incident wave here. And we can go through and rewrite this in this form. This is something that causes a little confusion for students. What we're doing is taking the magnitude of the complex of the magnitude of the product of two complex values. Well, the magnitude of complex number A times B is, in fact, the magnitude of A times the magnitude of B. So it's relatively simple to go through and take the magnitude of the product of two complex numbers. Now students say, well, gee, I did that once and you got mad at me and took off points. Well, that was when we were adding two complex values. The magnitude of A plus B is not the magnitude of A plus the magnitude of B, but the magnitude of the product of complex number A and B is in fact the magnitude of A times the magnitude of B. And so we're going to rewrite this numerator in this form as the product of the magnitude squared of our scattering matrix times the magnitude squared of A divided by 2. Well, that's simply equal to the incident power. And so we have a very nice result here. The power exiting or scattered from port N is related to the power incident on port M, on port 1 rather, by the magnitude squared of the corresponding scattering parameter. So again, for example, this were port 3, the scattered power from port 3, that would be equal to the incident power at port 1 multiplied by the magnitude squared of the scattering parameter S31. Again, this is only true because there's a single incident wave. If we have multiple incident waves on the device, we cannot use this equation. This really is something that is helpful to us. What it really says here, and this is kind of like reminiscent of the reflection coefficient, gamma L. Remember we said if gamma L had a magnitude squared of 0.3, that means that 30% of the incident wave was reflected. If the magnitude squared of gamma L is equal to 0.7, that means 70% of the wave incident on the load is reflected. And that's really what this is telling us here. If we have a lone incident wave on port 1 and no incident wave at either other ports, we can go through, if this scattering parameter parameter S31, for example, if its magnitude squared is equal to 0.2, that means that 20% of the incident wave at port 1 is going to be scattered out exiting port 2. Did the same thing for, let's say, port 3. If we did the same thing for port 2, then we would take this and multiply by S21, and let's say the magnitude square of that was 0.6. That means 60% of the wave incident on port 1 exited or scattered then from port 2. Now, if this is a lossless device, hopefully you see that in the end, if we add up the percent of energy that's scattered out of every port, it needs to equal 100%. All of the power incident on port 1, ultimately, if the device is lossless, must exit some other port, must be scattered out of some other port. So when we add up the percentages, it must be equal to 100% if we have a lossless device. So mathematically, perhaps this is a little clear. If we go through, again, for this experiment where we have an incident wave on port 1, but only on port 1, port 2, port 2, port 2, port 3, port 4, example, have ports that are terminated match loads, no incident wave on them. But I guess for a 3-port device here, what we can do is say that the power associated with the exiting or scattered waves is the sum of the scattered power of each, the scattered or minus wave at port 1, 2, and 3. Now, we can determine what this power is in terms of the incident power at port 1. We know that the power exiting port 1 is simply then the power incident on port 1 times the magnitude squared of S11. Likewise, the power exiting or scattered from port 2 is the incident power at port 1 times the magnitude squared of scattering parameter S21. And finally, the wave power associated with the wave scattered from port 3 is likewise this value. That's dependent on the magnitude squared of S31. And again, these magnitude squares, remember, they're going to be real values that are going to be less than somewhere between 0 and 1, like a reflection coefficient. And so they tell us the percentage of the incident power that is scattered from that port. If S11 is magnitude squared is 0.2, 20% of the incident power is scattered from out of port 1. If S21 is 0.6, then 60% of the incident power is scattered out of port 2. And then if the as the magnitude squared of S31 is equal to 0.2, then the remaining 20% of the power incident on port 1 is scattered out of port 3. In that case, if I add the 3 percentages together, I go through, and again, we're just pulling out using the associative property and pull it out here, the incident wave. The total exiting power from a device is simply the incident power, the lone incident power for this experiment, times then the magnitude squared of each of the scattering parameters associated with that first column, in this case, the column that has the incident power. That first column, that is the magnitude of that first column. We went through and talked about this. This is the value of the dot product of that first column with itself, with the complex conjugate on there. And if the device is lossless by conservation of energy arguments, that must be equal to 1. 100% of the power incident on port 1 must exit the device. If it's less than 100%, that means it's being absorbed by the device, and therefore it is a lossy device. If it's greater than 1, we have 120% of the incident power coming out of the device. Clearly, that's an active device. It's creating energy, or at least converting energy from some source into microwave energy. If it is truly a lossless device, this must be true. Now, we did it for port 1, but there's nothing special about port 2. We could have put an incident wave on port 2 and terminated the remainder ports in match loads, and we would have come to the same conclusion, albeit using a different column of the scattering matrix. We'd use S12 and S22 and S32. And so then our example of the 3-port device, the magnitude of the second column of the scattering matrix must be equal to 1. It must be a normal column vector. And likewise for the third column of the scattering matrix, it must be a normal vector. That column vector is normal. In other words, the magnitude squared of each element when added up must be equal to 1. And again, this is just a statement of conservation of energy. It simply says that 100% of the power incident on, in this case, port 3 will be scattered out of the device. not equally across the 3 ports, since we have 3 ports, but if we add the pieces up, it must equal the whole, the amount of power incident on port 3 in this case for this last column vector. So in general, we could write this equation for a lossless device. And of course, this is one of the equations that says that the columns must be normal vectors. So that was, again, the first statement for a lossless device. The columns of the scattering matrix are normal, and we can show why that needs to be based on a conservation of energy argument. We just did, hopefully, and you understand what we talked about there. Again, it's harder to see why these columns need to be mutually orthogonal to each other, but they do in order for it to be lossless, and we prove that mathematically. In this case, I just want to make sure that you recognize what we mean by a set of mutually orthogonal vectors. So here's the scattering matrix. Here's our column vector 1. Here's column vector 2, 3, and 4. And if we go through and we take any 2 of these vectors, take the complex conjugate of 1, doesn't really matter which one, we could do one or the other, take the complex conjugate of 1, but only 1, and then go through and multiply on an element by element basis. 1/2 times the complex conjugate of 1/2 times 0, plus 0 times this, plus 0 times that, times the complex conjugate of this times 0. Notice in this case, it turns out to be pretty simple. In every case, the product of 2 numbers turn out to be 0. So when we add 4 zeros together, we get 0. Those 2 vectors are orthogonal. One that's a little bit harder than to do mathematically is let's look at the second column and the third column. Again, we're going to go through and take the complex conjugate of these elements, and then we're going to multiply to the elements together, the like elements together, and then add them up. So we're going to take the complex conjugate of 1/2, which of course is 1/2, and multiply it by this. And what we get is j times the square root of 3 over 2. Now we go through and multiply these 2 elements together, they're 0. Multiply these 2 elements, they're 0. So we take j times the square root of 3 over 4, I should say, and then we add 0 to it and 0 to it, and we get j times the square root of 3 over 4. One more thing we need to add to it, though. We take the complex conjugate of this element, minus j square root of 3 over 2, and we multiply by 1/2, and then we get minus j square root of 3 over 4. Well, j times the square root of 3 over 4 plus a minus j square root of 3 over 4, of course, is equal to 0. So these 2 columns are likewise orthogonal to each other. And you can go through and take any pair of the column vectors and do a similar process, and you'll find that all of them are orthogonal to each other. They form a mutually orthogonal set of vectors. Every vector here has a magnitude of equal to 1. Verify that for yourself. Go through and show that this has a magnitude of equal to 1, for example. It doesn't really look like it when you first look at it, but verify that's true, making sure that take the complex conjugate of one vector before you multiply it by itself and add the elements together. And then likewise, we show that these are mutually orthogonal. This is the kind of scattering matrix that we would see for a lossless device. Moreover, this device would also be a matched lossless device. How do we know it's matched? Well, the diagonal elements are 0. So here's a scattering matrix whose diagonal elements are 0, it's matched, and whose columns form an orthonormal set, it's lossless. Also notice this is a symmetric matrix, that the off-diagonal elements reflect across themselves are the same. Excuse me. S21 is equal to S12. S31 is equal to S13, for example. And likewise for these elements here. So this is a symmetric matrix. And is there any coincidence or any thing we can infer by the fact that our scattering matrix is likewise symmetric? Excuse me. So what we infer from the fact that the scattering matrix is symmetric is that the device is also reciprocal. And so this is precisely the same as what we had for an impedance matrix or an admittance matrix. A reciprocal device resulted in an impedance or admittance matrix that was symmetric, where we had this form, all right, here, although we replace it with Z or admittance, transadmittance parameters Y. There. And so it's likewise the same for a scattering matrix. Of course, this is very different than what we had for lossless. For lossless impedance matrix, we just said the elements are purely imaginary. Where for a scattering matrix, we said the scattering matrix must be unitary and have orthonormal column vectors and so forth. So it's a lot more complicated. When it comes to reciprocity, exactly the same as the impedance and admittance matrix. The resulting matrix will be symmetric. All right, so we can write that in linear algebra form in this way, that the transpose of a scattering matrix is going to be equal to itself. Now notice this is not a Hermitian transpose. It's not like S31 is equal to the complex conjugate of S13. No, it says S31 is equal to S13. There's no complex conjugate associated with this equation, and therefore this is not a Hermitian transpose. It's simply a transpose to have a symmetric matrix. So just to summarize, again, we titled this presentation Matched, Reciprocal, and Lossless. A matched multiport device is a device that exhibits zero-value diagonal elements, not just some of them, all of them. Conversely, if we have a device whose scattering matrix has zero-value diagonal elements, all of them, it is then a matched device. A lossless device exhibits a scattering matrix that is unitary. The columns form an orthonormal set. Likewise, if we have a device whose scattering matrix form an orthonormal set, the columns form an orthonormal set, the scattering matrix is unitary, then it is a lossless device. And finally, a reciprocal device is one that creates a scattering matrix that's symmetric, and therefore any device with a symmetric scattering matrix is reciprocal. And so this example down here, again, if we look at it, has all of those characteristics. It's symmetric, so it represents a reciprocal device. It has zero value diagonal elements, so it is a matched device. And likewise, if you look at the columns, you'll find they form an orthonormal set, and so it is a unitary device, and therefore a lossless represents a lossless four-port device.